Hey everybody, again, I'm sorry I can't be there today. Now, here's the deal with today's stuff. It's just going to be a repeat of a lot of the things that we talked about yesterday. So if you have not done yesterday's stuff and you haven't looked at yesterday's video, you need to go back and do that. We are not going to be doing all the problems that are on the notes today. We're just going to be doing a couple of them and talking about kind of repeats of some things from yesterday. So again, if you haven't done yesterday's stuff, you haven't checked your answers yet for those odd problems, go do that. Think about this as just a little bit more of an enhanced experience. So what we're going to look at today is we're going to return to the idea of finding extrema, which are your maximums and minimums, using the extreme value theorem. The extreme value theorem says that if you have a closed interval, you are guaranteed to have at least one maximum and one minimum on the closed interval. Just kind of to remind you from yesterday, you can pull this out of your notes or you can look at the box that's right down here on your paper. In order to do that, to find your extrema on a closed interval, you need to make sure your interval is closed and continuous. You can do that by looking at the graph. You need to make sure you find your critical numbers by setting your first derivative equal to 0, and then finally evaluate your function at the critical numbers and the endpoints. So in order for us to do that, we're going to take a look at warm-up number 2 that's up here. I'm going to write it over on some paper so that it's a little bit bigger and easier for everybody to see. So this is warm-up number 2. And again, if you have not done yesterday's stuff, go do it now. Don't keep watching. Okay. So first thing is I have already graphed that on my graphing calculator. So I already know that it is a continuous graph. Remember, all you gotta do is just graph it. If you don't know how to do that, go back and watch yesterday's video. And I also know that my interval is closed. So I know that this is closed. So that's a little check there. And I know it's continuous because I checked it. All right. Now I'm going to proceed to find my first derivative. If you didn't notice already, that is a nested chain rule right there. So my first derivative goes as follows. This first piece is just power rule. You end up with 2. On the second piece, you're going to find the derivative of your inside, which is 2. And then you're going to find the derivative of your outside, which is negative sine. And then you just put your inside back in the parentheses. Now we're going to set that equal to 0 and we're going to solve it. Okay, so in order to do that, first thing I'm going to do is I'm going to bring this negative piece to the other side using addition. Keep those parentheses on there to hopefully help you out a little bit. Then I'm going to divide both sides by 2. Remember, if you need to, you can pause at any time. Now, in order to get rid of this sine positive 1, I'm going to have to use inverse sine. And then I'm going to need to divide both sides by 2. Okay, so because this is a trig function, it's probably easier for you to use your unit circle. There's only one spot on my unit circle between 0 and pi where sine equals 1, and that's up at pi over 2. So I have pi over 2 divided by 2, divided by 2 again, that's going to give you pi over 4. So when you are doing your test over here on this side, the points you need to check are 0 and pi because they're endpoints, and pi over 4. Now, if you want to reach for your calculator at this point and just get the decimals, you are not going to hurt my feelings at all. Go right ahead and do that. If you want to try it out with your unit circle, that's really good too. Remember to put them back in your original function, not in your derivative. So here's my original function. Let me slide back down. There's my original function. That's what I have to put them back into. So 2 times 0 is obviously 0. Over here, this will be cosine of 0, and at 0 radians, cosine has a value of 1. All right, now in this one with pi, that's going to give me 2 pi. And then if I come over here, that'll be cosine at pi, that's just 1. All right, now just kind of to remind you, pi is 3.14, so this is about 6.28 plus 1. So it's about 7.3 approximately. And then I've got to do pi over 4. So 2 times pi over 4 is going to be pi over 2. And then if I come over here, cosine at pi over 2 is 0, so that's plus 0, so that's just pi over 2. So that's about half of 3.14. I already know that's not going to be bigger than 7.3. It's going to be like, I don't know, 1.5 something. Yeah, 1.57, so about 1.6. All right, so from here I can easily tell that I have a maximum at pi, comma, and you can write it out as 7.3, or you can write 2 pi plus 1. I'm just going to write the 2 pi plus 1 because that's the exact answer. And I have a minimum at 0, 1. All right, and the extreme value says that that's what's supposed to happen. Let me scoot it up just a little bit so you can see the whole thing. And again, if you need to pause at any point, please do so. All right, so that's your trig functions. If you look at example A, it's just another trig function. It even has the cosine of 2x on it. So you should hopefully know how to do that one. So we're going to flip over to the back side of your paper. And we're actually going to look at problem C. So that's C. So that's f of x. And I'm going to go ahead and rewrite this as 4 minus x squared to the 1/2 power. And the interval I'll be working with is -2 to +2. Now, as I mentioned previously, you need to check to make sure it's closed and continuous. The closed should be pretty obvious. I mean, it's got brackets on either end, that makes it closed. Check. Continuous, how you're going to test that? You're going to go and graph it on your calculator and see that it is continuous. What does continuous mean? No holes, no gaps, no breaks. In other words, no asymptotes, no holes, everything works. All right, let's go find our first derivative. And if you did not notice, this is a chain rule. So I'm going to start by finding the derivative of my inside part. That is -2x. And then I'm going to take the derivative of my outside part. So that's 1/2 inside to the -1/2 power. So this needs a little cleanup. So I'm going to clean it up. I end up with -x. Because that is a negative exponent, it does go down to the bottom. And I'm going to change it back to the radical just because I think that's easier to think about. And again, if you need to pause, please pause so you have time to think about what's going on. All right, so we're going to set this equal to 0. Well, I've already kind of done that. And then we're going to solve it. So in order to solve this, you're going to multiply this piece to the other side. It magically vanishes. You get x equals 0. Now, why did I pick this problem? Because we need to kind of think about this idea. So down in the bottom of our problem, our first derivative, we actually just multiplied out a whole x variable. You're technically not allowed to do that. So in order to compensate for that, if you have a variable in the bottom of a fraction, which we have not really encountered that very much, when we set it equal to 0, you're going to have to set the bottom, the denominator, equal to 0 and solve that as well. And again, this will only happen if you have a variable in the bottom of your problem. If you don't have a variable down there, you're not going to set the denominator equal to 0 because that wouldn't make any sense. So to get rid of the square root, we square both sides. The square of 0 is in fact still 0. I'm going to move the squared term to the other side because it's currently negative. Then I'm going to square root both sides, giving me plus or minus 2 equals x. So as far as my test goes, I have to test my closed interval endpoints, which also happen to be the answers down here. Does that always happen? No. And I also need to check my critical number of 0. So we're going to take all of these values and we're going to put them back into the original problem, which, if you remember, is square root of 4 minus x squared. So first let's put the -2 in. Now when you square that -2, it turns back to a 4. 4 minus 4 is 0, and of course the square root of that is 0. 2, you're going to square the 2, that's 4 again. 4 minus 4 is 0. And finally, we're going to put the 0 in, and when we put the 0 in, that becomes 4 minus 0, and the square root of 4 is 2. Please notice I didn't put a plus or minus on it. That's because the square root was already there. I didn't put it there, unlike this problem where I actually had to square root both sides to solve it down there. All right, so extreme value theorem guaranteed that you would have at least one maximum and minimum. As you can see, we have a maximum at 0, 2, and we have 2 minimums, one at -2, 0, and the other one at 2, 0. So those are our maximums and minimums as per the extreme value theorem. Okay, so hopefully at this point on page 167, you have already done odd problems and you have checked them. So now you're going to go back to the same page and you're going to do some even problems. Please make sure if you haven't done the odd problems, please start there. The reason why, you can check the odd problems in the back of your book. Your even ones, you're going to have to wait till Monday when I get back to check them. All right, that's the extreme value theorem. You're going to be asked to use the extreme value theorem. That's what it looks like. And if you have any questions, just write them down so that on Monday we can go over them. And I will see you all on Monday.